Hello everyone, my name is Mingzhe Liao, and I come from Huazhong University of Science and Technology. Today I will present our paper about towards low-latency I/O services for mixed workloads using ultra-low latency SSDs. Here is the outline. Let's begin with the background. Internet service providers usually deploy their workloads in cloud data centers such as search engines, social media, online shopping, and so on. These workloads are latency sensitive. They usually need to satisfy SLAs, and these workloads require servers that can provide low latency I/O services to respond quickly to the client. With the advance of non-volatile memory technologies, ultra-low latency SSDs have emerged to deliver extremely low latency and high bandwidth I/O performance. The state-of-the-art NVMe SSDs, such as Samsung Z SSD, Intel Optane SSD, and Toshiba XL Flash, provide sub-10 microseconds of I/O latency and up to 3 GB per second of I/O bandwidth. These ULL SSDs have a potential to provide low latency I/O services and meet users' SLAs. However, to improve resource utilization and energy efficiency, data centers usually collocate throughput-oriented workloads and latency-sensitive workloads on the same server. When they co-run on the same server, the collocation interference will cause significant performance degradation for the latency-sensitive workloads. Because the I/O interference often occurs on multiple storage layers in the kernel, latency-sensitive workloads often cannot fully exploit the advantages of ULL SSDs. How to mitigate the cross-layer I/O interference between latency-sensitive workloads and throughput-oriented workloads in the kernel, and thus provide low-latency I/O service for the latency-sensitive workloads. This is the major goal of this work. To figure out the root causes of cross-layer I/O interference, in the following we will elaborate our motivation with experiments. Here we will briefly introduce our experimental setup. We use ShortDB as a latency-sensitive application and use a benchmarking tool, dbbench, to generate two workloads, read-random and fill-sync. We use Bayes as the throughput-oriented application, which performs machine learning tasks on Hadoop framework. We collect the response time of RocksDB when it runs solely and co-run with Bayes. As shown in the figure, the average response time of read-random and fill-sync in the co-running model increased by 1.5 times and 2.7 times compared with the standalone execute model, respectively. The 99th percentile response time even increases by dozens of times. To explore the root causes, we profile the execute time spent in the I/O stack for the read and write paths, respectively. The above figure shows the operations in the read path, which involved in several storage layers. We would like to emphasize the I/O completion. After the request is dispatched to the device, the I/O process is suspended. Upon the I/O completion, the blocked I/O process is awakened. Note that only when the process scheduler reschedules it can obtain CPU time to complete the following up work. Therefore, the read path involves in one device I/O operation and one process scheduling on the critical path. We break down the I/O execute time in the storage stack. As shown in the left figure, the time spent in the device and the process scheduler increases by 2.4 times and 5.5 times respectively. What happens at block layer and CFS scheduler? In the following, we will explore the root cause behind this experiment. Let's focus on the reason of significant latency increase in the device. We measure the average latency and throughput of Opton SSD using FIO benchmark. We can conclude the principle for using ULL SSDs from the figure. To obtain low latency, users should issue small requests and maintain a small number of outstanding IOs, and this is also enough to exploit the full bandwidth. However, BES generates burst IOs. In our experiment, the queue depth even exceeds 160. The right figure indicates that the latency is highly correlated with the queue depth. Besides, BES runs on the MapReduce framework and generates large I/O requests, which exacerbates the I/O congestion in ULL SSDs. Then we can conclude the root cause of latency increase in the device. Block layer is unable to limit the burst I/O to ULL SSDs. Now let's focus on the reason of significant latency increase in process scheduling. The figure illustrates the wake-up flow of a process. Once an I/O is completed, the interrupted core N will execute the ISR to handle the I/O completion. ISR will wake up the suspended I/O process, insert it into the running queue of the target core M, but the awakened process has to wait until it is rescheduled. CFS schedules the processes according to the virtual time. Usually, a process with a smaller wait time is scheduled earlier. To quickly schedule the awakened process, CFS maintains a priority pointer named next 2.8 so that it can be scheduled first in the following scheduling period. However, the awakened I/O process may be postponed when it co-runs with BES for two reasons. First, as shown in the right figure, the pointer next can point to PL only when the difference of wait time between the current process and the PL is larger than a given threshold. The threshold is too long relatively to the latency of ULL SSD. Second, the target core may wait a long time to begin the next scheduling period. Without a preemption mechanism, BES may run for a long time, and the CPU has no opportunity to schedule PL until an interrupt is triggered. We conclude that the reason for the latency increase of process scheduling is CFS is unable to schedule latency-sensitive processes immediately, even if they are awakened. Now we will discuss the write path. Buffered writes usually writes data from a buffer to the page cache and returns immediately. When an application calls fsync, the kernel actually performs write IOs to synchronize dirty data with the storage device. So we focus on the synchronous write path. The above figure shows the operations in the synchronous write path. Overall, one fsync contains 4 device I/O operations and 6 process scheduling in the entire I/O path. For statistical convenience and easy to understand results, we break down the I/O execute time into several parts, similar to read paths. As shown in the left figure, TD2 and Tscheduled increase by 15 times and 9.4 times respectively. The latency of other portions also increased by 2 to 4 times. Since the fsync path contains 4 I/O operations, root cause 1 can increase the time spent in the device, and thus increase TD1, TD2, TGD, and TGC. Since the fsync path contains 6 process scheduling of awakened processes, root cause 2 can increase the time spent in process scheduling, and thus increase the TD1, TD2, TGD, TGC, and T-scheduled. But we can find some deeper reasons. ext4 is the default file system for Linux, and using the ordered mode journaling, it commits a compound transaction for the target fsynced file. As shown in the figure, when the GBD2 thread commits the transaction of file A, the committing transaction includes uncorrelated inodes. The GBD2 thread must wait for the completion of the dirty data block write operations due to the ordering constraint of the journaling. So we can find that, first, the compound transaction involves dirty data blocks of other uncorrelated files, and thus introduces TD2. Second, GPT2 has to submit more metadata blocks, which also lead to a growth of TGD. Third, transactions are committed by the GPT2 thread rather than the fsync thread, and this introduces the wake-up of fsync thread and the GPT2 thread, and thus introduces the T-scheduled. We conclude that the root cause 3 for the increase of fsync path is that the fsync thread needs to wake up GBD2 to commit a compound transaction. Next, we talk about our detailed design. In order to solve the above problems, we propose fast response, a holistic approach for improving the performance of latency-sensitive workloads using ULL SSDs. It can deliver the attribute of latency-sensitive IOs through the IO stack, mitigate interference in different layers, and doesn't degrade the performance of throughput-oriented applications much. The first thing we need to do is to verify an I/O is latency sensitive or not in the kernel storage stack. We may also call latency sensitive as critical. As shown in the figure, we provide APIs for users to characterize the attribute of IOs. The attribute is delivered through the entire IO stack. We extend the data structures in different IO layers to pass the IO attribute. Let's discuss the scheduling scheme in each storage stack. We first focus on the block layer. To meet the principle for using ULL SSDs summarized earlier, we enhance the block layer. For issuing small requests, we try to split large non-critical BIOs. For maintaining a small number of outstanding IOs, we use tokens to limit the number of throughput-oriented IOs to the ULL SSDs. Each non-critical request is dispatched with a token, which is released during the IO completion. Thus, non-critical requests are blocked if there is no available tokens. In this way, the impact of I/O interference on latency-sensitive requests in the device can be mitigated. For latency-sensitive IOs, we enable them to bypass the I/O scheduler and dispatch them directly to the underlying layers. We also try to avoid significant performance degradation to the throughput-oriented applications. First, we configure the split threshold to 32 kilobyte and the token number to 8. This is enough to utilize almost the full bandwidth of the ULL SSDs. Second, unlike the BFS and the MQ deadline IO scheduler that use a global queue to dispatch all requests, we attach a dispatch queue to each hardware queue, and thus can fully utilize the high bandwidth through parallel dispatching. Third, we insert the split sub-requests in the queue in order according to their LBAs so that they can be dispatched consecutively. Now let's discuss the process scheduling. The process pointed by the pointer next, or with the minimum wait time, is scheduled first in the next scheduling period. To schedule the suspended critical IO process quickly, we should first begin the next scheduling period as soon as possible. Second, point the next pointer to the suspended IO process. Upon the IO completion, the interrupted core N executes ISR and wakes up the suspended critical IO process PL on the core M. We would try to preempt the current running process of the core M, so the core M can enter the next scheduling period quickly. As long as the awakened IO process is belonging to latency sensitive applications, we point next to it immediately, and thus enable it to be scheduled first in the next scheduling period. In this way, the critical IO process may be scheduled quickly after they are awakened. CFS is a scheduler that is fair to each process. Our process scheduling scheme has very little negative impact on the fairness, and it is impossible to starve non-critical processes due to the following reasons. First, the process pointed by next is scheduled only if the difference between its wait time and the minimum wait time is less than a given threshold. PL is not absolutely scheduled first in the next scheduling period. Second, the latency-sensitive application process is rescheduled according to our policies only when it is woken up. Normal scheduling is not affected. Now let's discuss the transaction commit. The figure shows different transactions commit in the file system. When a latency-sensitive process calls fsync, we provide file-level journaling and commit a file-level transaction to the fjournal area. We don't change the normal transaction in the default file system. The file-level transaction only includes the minimum metadata of the fsync file, which is the minimum information for the crash recovery. Owing to the file-level journaling, the latency of fsync can be reduced in three ways. First, there is no need to wait for writing back the dirty data blocks of uncorrelated files, and thus TD2 can be removed. Second, it reduces the amount of metadata blocks submitted, and thus TGC can be reduced. Third, the fsync thread itself is responsible for committing transactions, and thus avoids the cost of process scheduling for GBT2 thread and fsync thread waken up, so T-scheduled can be removed. The figure shows the structure of an F transaction. We commit the minimum metadata of the fsync file, i.e., inode structure and external extend blocks. Other metadata information shared among multiple files, such as GDT, block bitmap, inode bitmap, inode table, are not recorded. Since this information can be recovered using the normal transaction and the F transaction, the structure of an F transaction is similar to the normal transaction. Is composed of a header block, several metadata blocks, and a commit block. The header block includes some information of the current transactions, inode information, and block tags, which store the mapping between each external extended block and its actual block number in the file system. The commit block is used to validate the completion of an F transaction. Normal transaction can recover almost all file updates except the file A. We focus on describing the crash recovery of the F transactions. The crash recovery module scans the F journal area and reduces the valid F transactions in order. As shown in the figure, the recovery of the F transaction is redone as follows. File A can be recovered using the external extend block and the block tags. Dirty metadata blocks can be written to the right location in the device. Block bitmap can be recovered using the external extend block as shown in the figure. The external extend indicates the number 13 and 14 blocks are used, so we need to set the 13th and 14th bit of the block bitmap. Inode bitmap can be recovered using the inode number. The recovery is similar to the block bitmap. Inode table can be recovered using the inode structure and the inode num. New inode structure can be updated. GDT includes some description of the block group, such as the free blocks and the inodes, can be recovered using the new information of the block bitmap and the inode bitmap. Then we talk about our evaluation. Here is the experimental setup to elaborate our designs in different areas. We evaluate the following systems. A vanilla Linux kernel with default configurations is used as a baseline. FlashShare proposed cross-stack optimizations to reduce IO interference through the software layer to the device layer. Because our work focuses on software approaches for public available ULL devices, we only implement the software solution of FlashShare called Select ISR. The major techniques include bypassing the block layer and pulling IO compression for critical IOs. BOPT includes the block layer optimization. On the basis of BOPT, BSOPT adds CFS optimization. On the basis of BSOPT, BSGOPT adds file system optimization. We evaluate the proposed techniques by co-running the latency sensitive application and a throughput-oriented application. For latency sensitive application, we use RocksDB. It stores 40 kilobytes dataset with 4 byte keys and 4 kilobyte values. We use DBench to generate a read random and FuseSync workload. The workloads send 2,000 requests to RocksDB per second. For throughput-oriented applications, we adopt several applications selected from HiBench and Big Data Bench, including offline analytics, machine learning tasks, and web search. We analyze the performance of read and write paths using workloads read random and FuseSync respectively. For the read path, since read path doesn't involve the transaction commit, we don't evaluate BSGOPT. Compared with vanilla, BSOPT can reduce the average and 99 percentile response time by 36% and 77% respectively. For IO-intensive workloads such as tersort and index, BSOPT achieves more latency reduction compared to Select ISR. For the synchronous read path, we consider GPT-2 also as latency sensitive in BOPT and BSOPT. This is because transaction commit operation is on the critical path. Compared to vanilla, BSG OPT can reduce the average and NICE personnel response time by 58% and 83% respectively. Journaling optimization is domain for reducing the latency of a synchronous write, and works better with block layer and CFS optimization. Now let's discuss the impact of orchestration on the performance of the throughput-oriented applications. Although we aim to reduce the response time of latency-sensitive workloads, the performance loss for throughput-oriented workloads is reasonable, no more than 6% for all applications. Throughput-oriented workloads are oblivious to the latency of each individual request, but are sensitive to the bandwidth of storage device. The performance loss is very moderate. This is because, first, the number of tokens in the block layer ensure that almost maximum bandwidth of ULL SSDs can be utilized. Second, the redesigned CFS has very little impact on the fairness of process scheduling, and throughput-oriented applications will not stop. Third, GPT-2 can commit normal transactions, and this process is not blocked. We further analyze the root cause of latency reduction in the L stack. In the read path, select ISR removes the waiting time of process scheduling after process wake up, but not works well in IO-intensive workload, since the latency in the device layer becomes dominant. BOPT can reduce the latency in the ULL SSD owing to the request splitting and throttling. BSOPT can reduce the cost of process scheduling after latency-sensitive application threads are awakened, since the critical processes are prioritized during this time. BSGOPT can solve the compound transaction commit. There is no need to wake up the fsync thread and GPT-2, so there is notice scheduled. And fsync thread doesn't wait for the writing back of dirty blocks of other uncorrelated files, so TD2 can be also removed. There is less metadata blocks to be submitted, so TGD can be reduced. Finally, a summary of our work. In this paper, we identified the root causes of I/O interference on ULL SSDs for co-running workloads, including compound transaction commit in the file system layer, resource contention in the block device, and costly process scheduling. To solve the cross-layer I/O interference, we propose fast response, a holistic and cross-stack approach, and we optimize the block layer, file system, and process scheduler to mitigate the cross-layer I/O interference. Experimental results show that our solution can significantly reduce the response time of latency-sensitive applications when co-running with throughput-oriented applications using the ULL SSD, and the performance degradation for throughput-oriented applications is moderate. That's the end of our presentation. If you have any questions, please feel free to contact us. Thank you for attention.